Welcome back. Let's talk about protons and neutrons. So, Goldstein is our next scientist that you need to know. Again, we have a star, so this must be important. He observed that the cathode ray tube and found that there were actually rays traveling in both directions. And so the electrons traveled in one direction, but then there were some other particles traveling in the other direction. And so he concluded that those particles must be positive particles, and such charged particles are called protons. So it took a while after the electrons and protons before we discovered the neutron. And why do you think neutrons were more difficult to discover? So, the neutrons are a subatomic particle with no charge, but the mass equal to that of one proton. And so, a neutral particle is much more difficult to discover because we can't use charge to kind of separate them out. So, the proton, and we'll find out more about the nucleus in a minute. So we have the electron, proton, and neutron. So in this chart, which is one from your book, you need to know the first column, the second column, the third column, and you should just know the relative masses here, that protons and neutrons are equal, and electrons are very, very, very small in comparison. You don't need to remember that other 1/1840. So, although protons, neutrons are extremely small, theoretical physicists believe there are yet smaller subnuclear particles called quarks. But we are not going to talk about quarks in this class. What evidence did Thomson, and that's misspelled there, there's no P, that led Thomson to conclude the cathode ray was a stream of tiny negatively charged particles? You should be able to answer that question. And his evidence is that the ray was attracted to a metal plate with a positive charge. And so those two particles were attracted, so they must have opposite charges. When subatomic particles were discovered, scientists wondered how the particles were put together in an atom. So the first idea that was proposed was by J.J. Thomson, and it was called the plum pudding model. And that was that the atom had a uniform distribution of positive charge, and that the negative particles were throughout that whole positive area or volume. Similar to plum pudding, I think of it more like a chocolate chip cookie that would be three-dimensional. They're randomly throughout. So a student of Thomson was Ernest Rutherford, and he was awarded the Nobel Prize in Chemistry for his work on the atom and actually being able to disprove the plum pudding model. You don't need to know any dates. But Rutherford and his co-workers wanted to test the existence of the plum pudding model, and so they devised the gold foil experiment. So Rutherford's gold foil experiment. Again, I see a little star. Their tests use alpha particles, which is a helium atoms that have lost their 2 electrons. So it has a +2 charge, and here's the device that he used. We have a source for our alpha particles, and it goes through a slit to kind of focus that beam and hits the gold foil sheet here in one very small part. And according to the prevailing theory, the alpha particles should pass easily through the gold and only be slightly deflected due to some positive charge throughout the atom. What we found out, however, is that most particles passed straight through with no deflection. Some were slightly deflected, but then there was a surprisingly small fraction, however, of particles that bounced off the foil at very large angles, and some were even deflected straight back. So, scientists use this kind of information to decide how the atom was put together. And he proposed that the atom was mostly empty space, thus explaining the lack of deflection of most of the alpha particles. He also concluded that all of the positive charge and all of the mass must be concentrated in a very small region that has enough positive charge to account for the great deflection of some of the alpha particles. Because alpha particles are positive, they'll be deflected by the positive center. So his atomic model is known as nuclear atom. You need to know that vocab word. The protons and neutrons are located in a positively charged nucleus. The electrons are distributed evenly around the nucleus and occupy almost all of the volume of the atom. According to this model, the nucleus is tiny. It's densely packed when compared to the atom as a whole. If we were to compare this to a football stadium, and we're not talking a high school football stadium, but maybe a very large stadium like the Liberty Bowl or even the Titan Stadium, if the whole stadium, all the bleachers and everything were the size of an atom, then the nucleus would be a marble at the 50-yard line. That's pretty small. A lot of empty space. Rutherford's model turned out to be incomplete, and it was later revised. And it was to help us explain the chemical properties of elements. So, what evidence did he have? Well, you can read this, and I suggest you pause it. I'm not going to read it to you, but most of the alpha particles should have been deflected at small angles, but many were deflected at large angles, and so that discrepancy told them that it had to be a small, dense, positive center. Electrons in the structure of atoms. Atoms are positive. Protons and neutral neutrons are inside the nucleus, and the negative electrons are outside the nucleus. 3 kinds of subatomic particles. The nuclear atom, protons and neutrons are in the nucleus. Electrons are evenly distributed outside of that. And you need to know your vocabulary. Again, thanks for listening, and I will see you later.